Again, we're going to be taking a look at these equations where the variables and the exponents. Which, from previous lessons, means we're probably going to be dealing with what? Logarithms. Now, some of these problems you won't need logarithms. That's kind of the first half of the lesson. But then some of these you'll have to. Let's go ahead and start with this property of equality of exponential functions. It goes the following way. If we have a statement where we have a to the x is equal a to the y, notice our bases are the same, a and a. Our exponents are x and y. What do you suppose is going to be true about those exponents if the bases are the same? X and y has to be the same. Yeah. If it's going to be a true equal sign in between, then x is going to be equal to y. So this is the concept we're going to use to solve some of these. We want the bases to be the same. Therefore, if we have the equal sign in between the two of them, we can say that those exponents have to be equal to one another. You know, if I give you 3 squared is equal to 3 to the x, what does x have to be? It needs to be 2. It's the same concept. So notice for example number 1, we do have the variable and the exponent. We could use the logarithms, but if you're like me, you like to stay away from logarithms if you can. So let's see if we can't find those common bases here. We have 2 to the x. Now what I want to do is I want to rewrite 16 so it has a base of 2. Can we do that? Yeah. What is that exponent going to be? 4. Everybody agree that 2 to the 4th is 16? Still the same value, just looks different. Therefore, x is going to be equal to what? 4. Let's do another one. 9 raised to the c plus 2 is equal to 27 raised to the second. Nine raised to the c plus 2 is equal to 27 raised to the second. Now we're looking for that common base between the two of them. 9 and 27. What do you suppose that base needs to be?
Oh, never mind.
We could try 9, but 9 to the second power is already up to 81, which is way past 27. So could we reduce both of those down even further? Yeah. Suppose we're looking for that base of 3. You know, if I want to rewrite 9 so that it has a base of 3, what would my exponent be? 2. And if I want to rewrite 27 to have a base of 3, I would write it as 3 to the third. Let's take a step back and look at this. 3 squared is going to get us 9. 3 cubed is going to get us 27. I still have the c plus 2. I still have the 2. And again, the whole idea was to get that common base. So we can use this method. This is okay. Power to a power indicates we want to do what? We need to multiply. And again, understand parentheses are there. We need to distribute that 2. So 2 times c is 2c. 2 times 2 is 4. And 3 to the 6th power. Bases are the same. We have an equal sign in between. So now we can say that 2c plus 4 is equal to 6. Algebra the rest of the way. Okay with that idea? Now that we see it, we're okay with it, but it's not the easiest to come up with, I agree. Part C is kind of an extra problem. Let's go ahead and go through this one together. We have 2 to the t is equal to 1 over 16. You know, I think we all recognize that we could rewrite 16 to have a base 2 with an exponent. The only problem is it's in the denominator. Am I right? So what could I do to bring that 16 up to the numerator? Yeah, very good. Would this be the same thing as saying this? It is, yeah. You're just not used to seeing it that way. You're used to seeing it in this direction. 16 to the negative 1. And you've been programmed to be, oh, okay, negative exponents, I don't like them, so I'm going to move them down below. So therefore, it's 1 over 16 with a positive 1. Very good. So let's bring it up to the numerator so it's on the same level, on the same playing field. Let's keep that to a negative 1. That's okay. 16, now we're going to rewrite it to have a base of 2. What's my exponent? Hopefully you're saying 4 to the 4th power will get us 16 again. Power to a power, we multiply. Could we check it? Could. Okay, it's an equation. You can check any equation when you solve for it. You know, 2 to the t means now t is negative 4. Negative exponent rule. Bring it down below to make it positive. Sure enough, there it is, 1 over 16. And then we get to problems like this. 200 is equal to 1.05 raised to the power of x. Again, where is the variable located? In the exponent. And the method that we did first half of the lesson is try to find the common base. And you're probably seeing, you know, 1.05. It's probably going to be tough to find that common base working with 200. So the method that we did at the first half, it's not going to work here. So now what do we need to use? What do we use when the variable's in the exponent? One of the favorite concepts that we've worked with this year. Logarithms. If we take a look at 3 is equal to 3, you know, we can multiply both sides by 2 to say that 6 is equal to 6. That's okay. That's true, right? Okay. We could divide both sides by 4 and it would still be equal. We could square both sides and it would still be equal. Are we equal if we take the log of both sides? Yes, we are. Okay. So what we're going to do is we're going to take the log of both sides here. I'm going to say that the log of 200 is equal to the log of 1.05 to the x. And the reason we want to use logs is because that power rule. Because the power rule tells us to take the exponent and put it where? In front, right? What it does is it takes that exponent, that variable, and it brings it down to our playing field. Because I know what to do at this point. How do I solve for x? Well, I simply divide both sides by the log of 1.05. And yes, it's logs, but the good news is you have the calculators that can do that for you. Take the log of 200 divided by the log of 1.05. Make sure you put parentheses around those. Again, it's logs, so chances are you're going to get your irrational number. Answers that we're coming up with. If we round to the nearest 10th. Very good. Last one we're going to do. Where's the variable located? In the exponent, yes. So that means we could either look for common bases. You know, we have an e involved, so that's obviously not going to be the route that we want to go. Or we're going to have to use logarithms, right? Now we're using the number e here. So instead of the common log, we want to use the natural log. That's your hint. We're now just going to take the natural log of both sides. Am I okay if I do this? Is that the same? No, it is not. Okay? By putting parentheses around there, what I'm saying is that this base of 6 and the e go to the x. Well, per the statement, the only thing that the x goes to is that e, or the only base is e. So when you write this, be careful. It is the log 6e raised to the x. The x only goes to the e. And now, before we can bring that x down, what we actually need to do first is separate them out. We're multiplying between the two of them. So we separate them out with our addition property. And now that we're down to that single base, now we can bring the exponent down. And what's the natural log of e? 1. So x times 1 is just simply x. So how do I solve for it? Subtract that to both sides. And again, the calculator will take it from there. Answer that we're coming up with, round to the nearest 10th. Make sure you use the natural log button, not the log. Make sure you're able to come up with -0.2 or -0.18. So here's the whole point, in my opinion, in lesson 93. When the variable's in the exponent and they give you an equation and they want you to solve for that variable, what do you probably need to use? Logarithms. Why? Because it's that power rule that takes that exponent and brings it down in front and puts it on that same playing field where we can do our algebra from there. To me, that is the #1 reason why we do logs, or at least why we teach it in the high school classroom.